So today's class will be kind of the hand-wavy, motivation-y stuff, okay? Which I think is important. Because if you don't know why you're studying something, then why would you study it, right? So why groups? So my one-line answer to that eventually groups crop up in every field of physics and mathematics. Okay, so eventually, groups crop up everywhere in physics and mathematics, okay? And beyond. You know, groups are also being used in computer science. Well, computer science is really mathematics, so that's not surprising. So yeah, now historically, as far as I know, groups came from trying to solve the algebraic equation, quintic, the quintic or higher polynomial equations, right? And that is the subject of Galois theory. Some of you here have done Galois theory, I think. And, you know,
Yes,
yeah, and Galois, you know, kind of died in a stupid duel at a very young age. So, yeah, that's one of the, that's how, and I think also in the study of permutations, groups also arose in the study of permutations. And this is something that it's important for physics because of particles. When you have, you know, in physics, in thermodynamics, in statistical physics, in quantum mechanics, you know, you're counting stuff. And when you're counting stuff, you have to consider permutations. Okay, so that's how historically groups, you know, raise their very beautiful head, because I think groups are very beautiful. They're very nice objects. They're not horrible at all. They're just some of the most amazingly, you know, regular things. Even though this is outside the scope of this class, but I would encourage you to look at it. You know, this class we will be mostly concentrating on continuous groups. You know, so we will be concentrating on continuous groups. And these are also known as Lie groups. But when you think of the discrete groups and the finite discrete groups, there are some weird things that happen. And the weirdest of them all is called the monster. Okay? Or the monster group. And the number of elements in the monster group is roughly equal to the number of atoms in the Earth. So, and its representation, the monster group's representation have a lot of application in the field of modular forms in mathematics. So I encourage you to look at that because it's such a fun topic, but it'll be outside the scope of this class. Okay, so, you know, let's not get, you know, too distracted. So let's come back. Oh yeah, Otonu has posted in the chat a video about the monster from 3 Blue 1 Brown. Okay, so so the fact that the monster group, you know, that modular forms furnish representation of the monster group was essentially a set of conjecture, and that set of conjecture was called the monstrous moonshine conjectures. And they were made by famous mathematician John Conway. Okay, and John Conway died, I think, a couple of years ago. I think he died of COVID, and he was just this very amazing. He was just a very a great mathematician and a funny man. You may know of the game of life, which is a computer program. It's not a computer program; it's a game. It's what is known as a cellular automaton. So he invented the game of life, but he also made the conjecture that modular forms, furnish a representation of the monster group. Now, this remained unproven until a British mathematician, I think he's British, proved it, and his name is Richard Borchardt. He's still alive, and for that he also got the Fields Medal. And when I first started my PhD at Cambridge, Richard Borchardt taught a Lie algebra and Lie algebra course. And everyone knew that he was going to get the Fields Medal the next year. So everyone just piled into this one room to hear from Richard Borchardt what he thought about Lie groups. And and then he got the Fields Medal the next year. And Richard Borchardt used something called vertex algebra. A vertex algebra is very closely related to something called the kind of groups used in string theory called loop groups. Okay, so their vertex algebra arose, from the mathematics of string theory. Okay, so that's the story of the monster. So groups are very useful objects. Okay, so this is what I'm going to say. Groups are very useful. And the thing is that why do they arise? They arise because they describe often the symmetry or the symmetries of some mathematical or physical system. Okay, so this is what makes groups so useful. Now, in this course, we are going to use a certain connections that groups have with matrices. So, groups themselves are abstract objects. Groups are abstract objects. But every group can be represented by matrices. So this is the subject. So this connection I should say this is the subject. of representation theory. Okay, so what is representation theory? Representation theory is the theory of how, just one second. Representation theory is the theory of how to represent groups as in terms of matrices, okay? Now, often, the most important part of solving a physics problem or a related math problem is to figure out which representation is appropriate. Okay, the rest is kind of easy. Okay. Any questions? Okay, so the connection between the connection, so sorry, can someone speak up, because I'm not sure if turning on the do not disturb mode is going to affect okay, can someone speak up, unmute themselves?
Yes, you're audible.
Okay, awesome. Yeah. So somebody has asked a question, what are some other representations? Okay. Okay, so usually representation theory means that suppose you have a group and there will be an infinite number of representation in terms of matrices. Okay, so if you have some group, say G, and then you'll have a representation of this group, and let's call it represent M1 matrices. So this is a set of matrices, and there'll be another group which is going to be M2. Okay, another representation. Okay. So in principle, every group has an infinite number of representations. Okay, does that answer your question? Okay. And we'll see we'll see examples of this, right? So okay, Nahi is asking, can we always mathematically jump from one rep to another? What do you mean jump? Like unitary transfer? No, we cannot. They will be different dimensions. There are equivalent representation, there are inequivalent representation. If two representations are inequivalent, you cannot transform from one to the other. Okay, so the connection between representations and matrix representation and groups is very deep. So in fact, many groups are defined in terms of matrices. And this is the so-called fundamental representation or the defining, I think it's called the defining representation. So there are groups which are defined in terms of a set of matrices, and there are other matrices which are representation of that group. Okay, we shall see examples of all of this. Right? Okay, so this is the motivation, and let me just give you a very quick like list of applications of group.